All right. I know this is going to sound like I'm bragging, but it ain't bragging if it's true, and it's true. When I was in the Army, I worked on nuclear missile sites, and I took a great interest in the quantum, which was just starting to come around at that time. This is 1970. And I did so much research on this. Nobody's ever done as much research as I did. And I researched everything, because you had to research chemistry and heat and temperature and light and the whole nine yards. I ended up with this. The transfer of energy is from light to atomic vapor. Just like I said, out in space, it's atomic vapor. It hasn't coagulated, condensed. Below the atmosphere, the ionosphere, into our atmosphere, it condenses and it becomes. Now, and I also had this, there's only two types of intermolecular forces. There's dipole, polar and nonpolar. And then I explained every single thing. And I explained it. I didn't just say, oh, this is what it is, this is what it isn't. No. I went through everybody's laws, Millikan's oil drop experiment, all the laws and so forth. And I think Millikan has it right, that each electron weighs a certain amount. And that's the dipole electron, the black and white, which I'll be showing you in a minute. But it weighs approximately 0.005485 atomic mass units. One atomic mass unit is a proton. And you only get light, which is way down and it's stable. And then the next stable thing becomes a proton. All in the middle, it's unstable. And they can jiggle around and give off parts and take parts on, and that's how life changes things through nucleophilic invasion and substitution, using those spare parts. Okay, you have to understand dipole electron flood theory. Like I said, atomic vapor. Well, what is atomic vapor? Atomic vapor is like these little bits and pieces of a proton, the bits and pieces of them. They can be separated down into 1,839 separate parts. When they are in those separate parts, they have to attach to something. They're not going to just float around freely. They become heat, for one thing, which, let me show you what, this is what a proton looks like. There's a dark center. That is dark matter. Every proton has it. We're made of dark matter and white matter. The white matter bounces back, you can see it. The dark matter you can't see. That's the only thing. It's inside. It's inside. There's where the dark matter is, but you can't see it because it's completely coated by the white matter, and the white matter bounces back at you with a field. So you never can see that. You never ever see the dark matter. That's why they say it's here, it's everywhere, but we can't find it. Well, it's inside of every one of these protons. All right. Now, this is a proton, and it has approximately 1,839 dipoles. And I told you, well, let's see what the dipoles are and so forth. There's a white particle and a black particle. The black particles collect together in the center. They don't mind being on top of each other. The white particles don't want to be next to each other. But they want to desperately be attached to the black. So they always want to push away from each other, but they also always want to pull into the black. Very, very, really cool system. So you got your white electrons, your dark muons. Now, this is the difference in the standard model. Standard model has one big black center and a couple of little electrons around it. That's just not the case. It's the equal number, but the black goes to the center. I agree with that. Now, then the other smallest parts that exist can be separated. We did separate them. I'll show you that. But normally, you're going to have at least this. And this would have been normally what we call an electron. It's the negative portion with the positive, a gluon, they call them now. They know about them. They just don't realize 1,839 of them make a proton. Now, two gluons back to back, and I will show you this. I'm not just guessing. Make a photon. A photon is the smallest stable particle. It's stable. That's why they go through the air and they bounce off of things and they do all kinds of stuff. This is a stable particle, but it does not want to exist on its own. Light wants to exist on its own. It doesn't want to take any more in. It's equal. This is not equal. This wants something to bond with, which means heat. This will invade things and cause heat. And when something heats up, if it's a solid thing, and it heats up and doesn't expand, it becomes heavier. Heat has that black particle, and that's where the weight is. Remember I said I'm going to show you in graphic detail, but this right here is a photon. That's from a light, from a laser. Use CMOS. It's now accepted. Everybody's using it, CERN and all of them. And the white particles can get bigger or smaller, as seen right here. This is this. That's how much energy that one has. Not much compared to this one. This one's getting bigger because it's coming through here, crashing with all the other particles that are in front of it, causing glow. Whenever a particle smashes into something, it glows. Sometimes it glows just a little bit, sometimes it glows a lot. Depends on how fast the particle coming was and what it hits against. Those are the two things. The fields oppose other fields. All right, now I just showed you the particles that we found. That was done with this smartphone, a Samsung Galaxy S3 from 2012, and a Bosch measuring pulsed red laser. We did this, and we created photons. Okay, this is what Fermilab, CERN, all of the big labs do. They smash protons into neutrons head to head, and they get all this debris. X just means it could be a chunk of who knows what. These are the smallest particles they see. They don't realize it, but these two things here are not just a big solid thing with a couple of quarks in them. There's 1,839 of these, so they go flying everywhere when they smash these. It's a mess. They call it a particle zoo, and it is. This could be that big. It could be this big. Every one of these is a dipole electron. And you don't have to have them exactly at the right quantities to become like iron and magnesium and calcium. There can be all kinds of different varieties of calcium, magnesium, everything. Every different atom. Okay, here they get bigger and bigger and bigger, but in semi-stable quantities. So if you came up here to iron, let's say Fe, let's say it had 10,000 would be stable iron. Well, you could go down to 9,500, which means you're missing 500 of these particles. And it's still called iron. And you can go up to probably 10,000 or who knows what, and you're still considered iron, but you're on an isotope upwards level and an isotope lower. That's what makes life work, is nucleophilic invasion and substitution. And they just don't realize that this is the particles of life that fuse into cells and do all the kind of things to construct and destruct. They do everything, these particles. And these are the particles I just showed you. Instead of seeing them, these huge chunks of stuff, we could see them actually in their smallest nature, which is this. Instead of this, which they see going everywhere, we see this, which is one of each of these, a black and a white, and they're dipoles. So even though I'm only showing two particles, each one of them is a magnet, and they're glued together just like this. All right, so they have a black and a white and a black and a white, and they're solid together. I mean solid. You can't break those apart, except for what we did was put them through the Venturi over here. When we put them through the Venturi, very simple process, we got completely raw white energy. And I mean, that's extremely explosive energy. There's no other way to look at it. Increased luminosity means increased energy. You just look it up. There's no way to deny this. All right, so here we go back to 2013. His Fermilab is showing the same particles we found, only they see them separated, and there's always a glow around the black one, because the black one is dark matter. All it can do is stop the light from hitting you. We found the exact same thing. That has all the mass, that has all the energy, and virtually no mass. It's just it can get big and small, as I have shown you in the other pictures. And that's from Fermilab now, 2013. So that's the Fermilab, right from their article. That's the picture, Fermilab point particles. The black one always has the glowy edge, and this one just glows and has no mass. That has all the mass. That's exactly what we found in our photons. Remember these two. Remember the glowy edge. Why would it have a glowy edge? Well, I can tell you why. Because it's just dark matter. It has a glowy edge around it. So does the green. They all do. And the other ones are just glowing, and they can be little and they can be big. This is coming through the air this way. That's why you see these little glowy particles here, because it's banging into other fields, charging up. That's what happens when something hits something else, it charges up. This one's being diminished because it's got this glowy one, black one in front of it, so it doesn't get hit by the particles. Eventually that will charge up and flip to the back, and that one will come to the front, and it will charge up, and then it'll flip. They call that the muon wobble. And it's exactly what we found. Here is it right here. This is what they talk about, muon neutrinos and electron neutrinos stuck together. And when they hit heavy water, muon goes its own, and the electrons make showers. That's exactly what we got. Only we didn't have to use heavy water. All we had to do was restrict it to a Venturi. And then those particles came back together. Now, when I presented this to Fermilab, because I found their article, I saw this article, where was it? And I said, wow, we found these particles. They do exactly what they say. It has a glowy edge. It's the black one, the white one, blah, blah, blah. We're using light so we can see them using CMOS. Now, CMOS is designed to see this size of a particle. I don't care how energetic it is. The particle itself gives off the energy. The energy is only a certain amount of energy you can get out of a particle. There's only, that's something I have to look into deeper. But there's only, I don't think one little electron can give you so much energy that it's going to destroy the CMOS, because it didn't. We used this regular CMOS phone. Didn't hurt it. So I reported this. I said, we can see these using a CMOS. And it was not received well at all. And I was really assaulted for making these statements. However, I did take a class at the University of Geneva back about 2015, something like that. And I explained to them exactly what we did. And we see your particles, but we used light. We didn't use your big, gigantic particles. We used CMOS. And no, you can't do that. CMOS won't work. Well, I finally convinced them it would work. And they did finally agree. And now, actually, CERN is using CMOS. CERN uses specially adapted CMOS sensors to detect particles. Well, especially adapted in some cases to reduce the extreme radiation when they're using big chunks like this. Because if you get hit by this, it's going to smash the CMOS. Absolutely. That's what they said. You're going to do too much energy. No, I said it's too much mass. Energy is not the problem. It's the mass. So anyway, they're using from regular cell phone cameras. Exactly what we did. New type of detector, 2025. They announced a breakthrough using innovative detector called optical photon antimatter imager. Well, for smartphones. They use an array of 60 modified smartphone cameras. And I reported this to CERN at the University of Geneva. They're like one unit. And they didn't disagree when we were done. It was a struggle to get them to listen, but by the time we were done, I prevailed. And it's consumer-grade CMOS sensors. They took away some of their color filters and micro lenses removed. And I have a friend that's doing, well, I'll show you what he's doing. You see this? That's some serious stuff. He's got a 5-inch Newtonian telescope with all kinds of little gizmos attached to it, and some special CMOS detector, which is from a smartphone. And he's stripped away some of the things, and he's got layered and images and all this kind of stuff, which I don't understand, so I'm not going to pretend I do. But I'm starting to learn. And but everything that I have found, it supports dipole electron flood theory, first of all. It supports the fact that light is vapor, atomic vapor. And here's what happens. This is a solar eclipse, so the moon is over the top of the solar disk, so we're not blinded. Now, what's all that stuff? That stuff is going, leaving. It's not coming back. It's not looping around. Some of it is. Some of it is right here, but not most of it. Most of it's going, and that's atomic vapor. And guess what else they said at Fermilab? The same guy, the same date. Where is it? Here it is right there. This is the same, I mean, I think it's like the same day. 2013, empty space isn't empty. You see that? Empty space isn't empty. He says it's like the head of a root beer. It's foaming and fuzzing everywhere out there in space. It's not empty. I agree with that 100%. And like I say, I can't see how they could have missed what I was showing them. I was very specific. I was very clear. But that's what happens. Now, so what else can I show to prove what I'm saying about the layering? This is the Earth. And it's spinning, and it's a globe, and it's going around the sun, and it's actually being dragged through the Milky Way. I'll show you that in a second. Now, what are we seeing here? What's this? That's the atmosphere inside the firmament. Call it whatever you want. I call it the ionosphere. And inside the ionosphere is the condensed water vapor, basically. Up in this area, it's basically more or less waterish vapor, and it condenses and rains on Earth. Well, out here, it's water, the same vapor, atomic vapor, but it's above the outside layer of our atmosphere. That's the outside layer of the atmosphere, and this is the thickness of the atmosphere. And out here, it's thousands of degrees. And you say, whoa, that can't be. Why? It should be real cold. No. This is where it scrubs through space. This is magnetic fields here, scrubbing magnetic fields here. And when you scrub and push and force against magnetic fields, you get glow and you get energy and you get really a lot of heat. Thousands of degrees. I'll show you the graph. Hold on a second. All right. This is the outermost layer, very low density. We're almost into space, which has low density. I'm not disagreeing with that. But then you get to this layer right here, which is the ionosphere. Here, ions mean single particles. Basically, they're these single particles. And they're just out here hotter than hell. And they're looking for something to attach to. And when they do, it creates a ton of energy. That's why lightning, static, electricity, it's the white jumping back to the black. And that's what happens when meteorites and all that stuff come through here. It's hotter than hell. It's 1,500 degrees Celsius, at least. And it's higher than that most of the time. That's why it destroys meteorites and all that business. Well, guess what? Right below that, it's the coolest layer of the atmosphere, minus 80 degrees Celsius. That's minus 112 degrees, I think. Why would it be here to here? It's so hot here, it's so cold here. What's going on? That is the dipole nature of these particles. And we're scrubbing out here, and then you have to have a dark attached to the white. And the dark is cold, has no energy whatsoever. Dark has zero energy, it pushes. And it's gravity. All right? Then below, you get up to warm again, where we are, down here, and the Earth has to absorb that heat. Now, the same thing happens on the sun. The sun, you know, is not hot. And actually, it's not hot compared to its corona. All right, so remember, here we are on Earth, and we have our outer atmosphere ionosphere, which is thousands of degrees. Well, the sun itself is approximately 10,000 degrees on its surface in that area. And they can measure these things. I'm not discounting that. To come out to here where it hits the ionosphere, it's millions of degrees. They have no explanation for that whatsoever, how it goes from 10,000 to millions. The same thing with here to out here. They just can't understand it. They did a tether experiment in our atmosphere. All right, so what they did was they took a tether. When I say a tether, that's just a big long line. And they unfurled it from a satellite in this layer. And this tiny little wire, which let's say it's going to be even 6 inches across. And when they unfurled it, it glowed for miles. It had so many of these electrons trying to get at that, and then it exploded because it couldn't handle the energy. They were trying to tap energy off of this layer because it's nothing but electrons. That's just nothing but electricity. But I produce nothing but electricity using the Venturi. That's nothing but electricity right there. Pure, raw electricity. If you could harvest it right here before it recombined with the black, I don't see any reason we shouldn't be able to have basically free energy. And again, they all started using the CMOS now. They realized I was right about it. That ain't bragging if it's true, and it's true. And again, this goes back 12 years. Both of the actually seen it, identical same particles. And I think the dipole electron flood theory should at least be able to be presented. And I am not able to get anybody to look at it or comment on it or help to get it seen. So, but I do have people now that are working. Look at this. This is Mason. This is incredible. And there's the dark matter, near glowy white matter. I can see dipoles everywhere. Dipole, 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 everywhere you look. Whenever you got a glob of dark, you're going to have a glob of white, dark white. Dark white. They don't have to be perfectly ball to ball like I see in the light particles, but they are dipoles virtually everywhere. If you look and you think carefully what you're looking at, you can see all the dipoles. See it? Dipoles, dipole, 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 dipole. They're everywhere. You can't miss them if you start. You got to start to look at things a little deeper than we've been told. They brush it off and they say, now you're trained because space is just like that. Well, first of all, light is going to slow down coming through that. I don't care what anybody says. When we can speed up light, that's not supposed to happen. Light, it will slow down. They know that. But they say, it has to have an atmosphere in front of it to slow it down. Well, duh. Who could say that's not an atmosphere? Who could say that's blank space, that light should never slow down? Obviously it's slowing down. They say that everything is expanding, pulling the light so it makes it look like it's slowing down. No, it's just slowing down. So it's time to relook at all this stuff. I want to be part of this. I've done the research, and I've got people behind me now that are finding things that nobody's ever seen. Look at that dipole. I think that's Saturn. I'm not sure. This is Mason again, but he's absolutely phenomenal stuff. You should see some of them. I mean, I got a bunch of stuff now from him. I believe that's the sun. And you see all these dipoles there? But this is stacked layering. Now, I don't really understand it. I really don't understand it, because I asked him, I said, what about all this stuff over here? What's going on there? And he's got a 5-inch Newtonian lens. Now, is this outside the lens? What's showing up there? Very crisp line around here. And it's a little more dense, so I don't know. There's a little bit of a difference here to here. Why? I don't know. These are the things I want to ask and find out about. But I see nothing but dipoles. It's just nothing but dipoles. And the same thing, Dylan found the same thing many years ago. This one, I gotta admit, freaked me out and still does. I have no idea what to think about this up here. This was just from a regular cell phone. I don't know what else he did. This was from Dylan Carpenter. He's in New Zealand. He's related to Rod. I think Rod is his uncle. Rod Warren did virtually all the other pictures. I did some, but nothing like Rod. And nothing like this. I don't know what to think. What is going on up there? Je ne sais pas. I do not know. I think I understand the blue. I understand the magnetic fields, I believe, and everything's a dipole. They're all dipoles. There's nothing but dipoles. And they collect in different ways to create different, whatever that is. I don't know. I have no idea. But if we're looking out, and that's the moon, which it is, and we're seeing these glowy things either on top of the moon or between the moon and us or somewhere in our atmosphere, but it looks to me like this is focused way out. So could it be in our atmosphere? I don't know. But whatever it is, it's strange. And that, my friends, is stranger. Okay, so why is it so important we even care about these two little particles? They don't even get stable until they get to be a big one like this. And there's 1,800 and so such and such. However, they're not really stable always at that particular point. I'm going to show you what stability means and how life works and why these are so important, because these are the basis of enzyme reactions which create nucleophilic substitution and invasion and life. Without enzymes and the ability to move these two little particles around, you'd fall over dead. Enzymes are 100% of the processes in life come from enzymes. All right, this is really serious, because we need to be able to use those little tiny bits to work with enzymes. Enzymes work extremely fast. Some of the fastest enzymes, like carbonic anhydrase, catalyzing reactions up to 1,000,000 times a second for digestive enzymes. That's to digest your food. For digestive enzymes to begin working almost immediately upon encountering the food source. The food hits them, they break them, just instantaneous. Some noticeable effects happening within minutes. The overall process taking several hours to digest your food. And that's all because of enzymes. And enzymes are from bacteria. So if you don't have good, healthy bacteria in your gut, you're not going to have the enzymes. You're not going to break down your food. You're going to have digestive issues. You're not going to be healthy. All right, this is my area. I understand this better than anybody breathing oxygen. Just a fact. All right, don't freak out. This is extremely simple. Iron is not just iron and it's always one ball exactly the same. No. Iron can be that much iron. It can be the same molecule, but only this much, which is an isotope. Isotopes are distinct nuclear, means the nucleus, species of the same chemical element. All they do is they don't have quite enough to be stable, which is in a stable range. They're too small or too big. And how many is there? Well, they've defined 28 different states of iron. All of these. Look at this. All of those are different irons. And all they are is one or two of these particles missing, or 5 or 10 or 20, or too many. It's having too many or not enough. And what happens with enzymes in your body is they come in with an enzyme and they break these little things into little tiny bits and pieces, and they throw off a half a dozen of these and add an extra 12 of those, and they turn all the things in your body into different stuff that your body can use to create life. That's what an enzyme does, and I don't think they understand this. All right, this goes back a very long time for me. Nucleosynthesis. They're talking about meteorites because they think they got changed because of coming through the atmosphere, and they will. You could change stuff, yes. Okay, they're talking about most of the work on iron was looking at meteorites, how they think they changed coming through and changing their states. But recently, mass spectrometry have allowed the detection and quantification of minute, naturally occurring variations, stable isotopes of iron. Much of this was driven by Earth and planetary science communities. Those applications to biological, this is where I'm going, and industrial systems are beginning to emerge. I'm looking for the biological. These are the different states of iron that are changed by enzymes in the body of a creature to create food, immunities, all of that stuff. Now, these are isotopes. So I'm going to show you something else about isotopes. Hold on. Now, they're talking about, there are 35 metals that are of concern to us because of residential occupational exposure. Well, they're saying 23 are heavy metals. I'm going to tell you something right now. Virtually all these transition metals, as far as I can determine, are in blood. They did a survey somewhere, I can't remember where it was now, but they took, I think, 100 and something very healthy people, and they tested for 26 different metals and metalloids that were in their blood. Now, what do those things do? Why are they in your blood? Are they bad for you? Are they good for you? I can tell you what they do. They do transitions. They're transition metals. They change things. They move molecules around in your body. And they do it by using enzymes and isotopes to do 1,000,000 years worth of chemistry in less than 1 second. And the only thing that stops them from doing their job is if they can't get to the substrate. They will do it instantly when they hit the substrate. It's called click chemistry. Go, yep. It's just like lightning hitting you. It's done instantly. All right, I believe I showed you some information. All right, this is click chemistry, and it's a method for creating complex molecules through simple, fast, reliable reactions, have high yields and few byproducts. That's catalyzed. You see this? Example is a copper catalyzed reaction between this azide and an alkyne to form a triazole ring. It's an enzyme that creates these very, very high yields and very few byproducts, but they're basically natural products created by the body to break things down. Now, they're going to be using it for drug development, material sciences, chemical biology, and I think I got the Nobel Prize for it in 2022 about click chemistry. Now, I've been looking at this. I always called it click chemistry myself because it is. As soon as it hits, it click. It's done. And it talks about connects molecular building blocks like building with Legos. And I'm going to show you. Let me just show you.